Guys, welcome back to the channel again. Let's try to understand another problem and try to solve it. So today's problem is from LeetCode 417, Pacific Atlantic water flow. So this is again in the line of similar problems that we have solved in the previous videos, where the rotting oranges and the walls and gates from in the same line. The approach will be pretty similar. So let's see what we are being asked. So there is an M by N rectangular island that borders both the Pacific Ocean and Atlantic Ocean. The Pacific Ocean touches the island's left and top edges. Basically, this is the island, left and top edges, they are touched by the Pacific Ocean, and the Atlantic Ocean touches the island's right and bottom edges. Okay, the island is partitioned into a grid of square cells, and we are given M by N integer matrix heights, where the heights RC represents the height above the sea level of the cell at coordinate R and C. The island receives a lot of rain, and the rain water can flow to neighboring cells directly to north, south, east, and west if the neighboring cell's height is less than or equal to the current cell's height. Water can flow from any cell adjacent to an ocean into the ocean, right? So we need to return to the two-dimensional list of a grid coordinates the result, where result I is equal to Ri and Ci denotes that the rainwater can flow from cell Ri, Ci to both Pacific and Atlantic Ocean. So we are given this example. We'll look at this example in the whiteboard. Basically, we are given this grid from which of the cells the water, if there is a rain, the water can flow both to the Pacific and Atlantic Ocean. That's the problem statement. Let's look at the constraints. So M and N, there we can compute them from the dimensions of the height grid, and the M and N can range from 1 to 200, and each this height can range from 0 to 10 power 5. Let's see this example and try to understand this in the whiteboard. Okay, so let's try to understand. So we have two borders of four sides of this grid. So this is basically overall, this is an island, right? So this island, and the top and the left side, they are touching the Pacific Ocean. This is the Pacific Ocean, and right and the bottom is touching the Atlantic Ocean, right? So what we are being asked, so the island has a different dimension, different heights, right? For example, water can flow from higher elevation to the lower elevation if there is a rain, right? That's intuitive. And we are also being asked that we need to return this any cell that from which water can flow both to the Atlantic Ocean and the Pacific Ocean. We need to return the list of the coordinates, right? So what we can see by just looking at the problem, so all of the cells bordering the oceans, so water can flow to them, right? So for example, this and this, all of the cells on the top and the left, water can easily flow to the ocean, right? To the Pacific Ocean. That is given, right? That is given. And all of the cells bordering the Atlantic, water can flow, right? So this, all of them, water can flow. So these are given, right? But, and also there are some middle cells that we need to compute from which one of those the water can flow to both Atlantic and the Pacific Ocean, right? So initially we can start from both of them. Let's say initially we will start adding the elements. We'll have to do this twice. What I mean with this, we'll have to iterate this grid twice. Initially, we will get the set of cells from which water can flow to the Pacific. What are they? So as I showed, they are these elements, right? These elements. So the approach will be similar to in the case of Atlantic. Let's just first review the Pacific. So this top row and the left column 0 and row 0, they are guaranteed that water can flow to the Pacific, right? Then after we get this one, we'll add them to the queue. To the queue, we'll just call this Pacific queue. Then we will do the BFS, breadth first search, from each element, from each cell. Let's see, from this we can go from the first one, right? First one will be in the queue, which will be this is 0 0, right? 1 2 3 4, 0 1 2 3 and 4, right? From the 0 0 element we can go to 4 directions. We can go to top, but it's already outside, right? We can go this, but it's already in the queue, because this one will be adding in the queue. And this one, right? This one it's already in the queue. So we are done with this, right? Then we'll just go the next in the queue. After we process this one, then we'll just look at the element 0 1, right? From here we can now go to top because it's a border, and this, and we can go this one. So after we check this one, can we check if water can flow from this cell to this cell? Yes, because the height is equal to this, right? Or it should be equal or more, right? Then water can flow, right? Then we'll add this one to the queue. And that's it. And we just go to this cell. All of these guys are in the queue. After we pop this, then next cell we pop this one. After we pop this and we check its neighbors, can water flow from this cell to this cell? Yes. Then we add this one to the queue of the Pacific queue, right? Then here we go here. Can water flow from here to here? Yes, water can flow. We pop this and we add this one to the queue. And from here, we just look at this one, right? Can water flow from this to this? No, we cannot. But this cell is also adjacent to this cell, right? To this 4, right? Water can flow to this direction, right? So right now we're not going to add this because we're just only checking this cell, right? The 0 4. And we cannot add this, but in the next process we can add this one. And then we'll just check this one. We see, can water flow from this to this? But it cannot, but water can flow to this direction. So we cannot move, we cannot do anything with this cell. We just simply pop, right? And the next one, this one, right? So after we pop this one, this is 4, water can flow. So we add this one to the queue. Then we go process this one, this cell 3 0, water can flow from this to this, right? Then we go to 5, and 5, water cannot flow, right? So this is gone. We will not add this one to the queue, right? Then this is done. Then all of the top is popped, and this one is also popped. The next element to pop is this one, right? So this is already in the corner. It's already processed water, and this is already in the queue. And this 3 can flow, and we pop, and we add this because the neighbor of 3, right? And this one we cannot because this is already outside, right? The 3 is less than 4. So these elements up to here can flow to the Pacific Ocean, right? So all of this is basically the boundary. All of the cells, the water can flow to the Pacific. And this one and the next cell, so we will check. Water can flow this to all of the cells neighboring to the Atlantic. Water can flow, right? Water can flow to the Atlantic Ocean. From this, we'll add all of them to the Atlantic queue to process, right? Then we start the BFS. Can water, from here, can water flow? No, we cannot flow, right? But water can flow from here, right? To this. So we pop this, and we add this one to the queue. Then after that, we pop this one. Can water flow from 3 to 1? Yes, water can flow, right? Then we pop this one. Can water flow from here to here? No, water cannot flow, right? Because this is a smaller, this is a higher, right? This is a lower level, this is a higher level. Then after that, this is in the corner. We cannot move anywhere. And this 2 top is, yes, here actually we can move from this one, right? This 4 is bigger than 2, so when we pop 2, we can add this one to the queue. And water can flow from here to here, and water can flow from here to here. Water can flow from here to 2, to 1, also to 3, and water can flow from 7 to 1. Water can flow from 6 to 5 and to Atlantic, right? That's the direction it's going. And after 6, we check. Can 2 flow to 6? No, we cannot flow. Can 4 flow to 7? No. Can 4 flow to 5? No. And can 3 flow to 4? No, we cannot. So basically, this will be the border where we can flow. The all of the cells from this bottom can flow to the Atlantic Ocean, right? So you can see there are a set of elements that from which water can flow to both oceans, right? What are they? They are basically, you can see they are this cell, right? Let me just change the color, maybe black. Yeah. So from this, water can flow, and 4, 5, 7, 6, and 5, right? Because they are basically sharing all of this, right? These cells, from these cells, we can flow. Water can flow to both oceans, right? So what we do, we initially add, as I showed, we initially add all of these cells. We're gonna run the BFS twice. Initially, we will collect all of the top row and the left column to the queue, Pacific queue, and the right one and the bottom one we're gonna collect to the Atlantic queue. Then we start processing, popping this each element from the queue, each cell from the queue, and try to do the BFS. And in the BFS, we are going to keep visited as a set. visited Pacific, and visited set for Atlantic, right? Then at the very end, after we do the BFS for Pacific, after we do the BFS for Atlantic, then we're gonna, this two BFS function will be returning, this is a Pacific visited and Atlantic visited. Then what we are going to get, we'll just get the P visited and A visited, right? Visited, this will basically the set. This will be Pacific set. This will be Atlantic set, Atlantic. This is a Pacific. And we are going to get the set wherever they are basically intersecting, right? So we need to return this this section where they are intersecting. So at the very end, we just get this, and we need to return as a list. So basically, we just return as a list. So let's look at the code, and it will be much easier. Okay, so this is a code. If in the line 5, if the heights grid is not given or it's empty, so we need to return the empty list. Then we compute the number of rows and number of columns from the dimensions of the heights grid. Then we define the directions, because we need to go from each cell, we need to go up, down, left, and right. Then, as I said, we need initially for the top row and the left most row, the column, we need to add to the Pacific queue, right? So basically, we are adding the 0 is a row and a column for all the columns, right? For all the columns. And the plus row should be in the row, this one, right? From here up to the last one. So we are adding the left most column, right? And that's how we are constructing the queue, initial queue for the Pacific. In the similar fashion, this way we're going to construct the Atlantic queue. And the Atlantic queue will be the same. We need to add the rightmost column and the bottom row, right? Then we're gonna, starting from those queues, we will need to construct. Yeah, we'll need to construct the set by running BFS. So in this BFS function, we have from this BFS function, let me check. From this BFS function, in the line 16, we can see we will pass this Pacific queue and the heights and rows, number of rows and columns, and Atlantic. To get the Atlantic set, we also run the BFS. We pass the Atlantic queue and heights and columns, rows and columns, right? Then at the very end, and we need to return this. We need to return the list of Pacific set and Atlantic set. So let's see this BFS function. So in the BFS, we are going to pass the queue and the heights and rows and columns. And we initialize the visited as a set, because we don't want to visit the cells once we visit them, right? Then while queue is not empty, then we pop that queue initial element, initial cell, row, and column. And if row and column is already in the visited cell, and we just pass, we go to process next element in the queue, then we add, if it's not, then we add the row and column to the visited cell. Then from that cell, we need to traverse, check all 4 neighbors, right? Top, bottom, and right and left by this line 32. Then we compute a new row and new column. This is the loop, right? For direction. Then we check if the new computed row is within the boundaries of the grid. and if the new column is also within the boundaries of grid. And we need here we are checking if the new row and new column, that cell, its height is bigger, right? Bigger than the heights of the old row and column, right? In that case, we add the new row and column because that's the cell we can water can flow to the either ocean, right? So this queue will basically finish traversing entire grid for for each ocean, right? So I mean, we're going to run them like separately, but initially we'll do this for the Pacific, then we'll do this for the Atlantic, and at the very end, it will be returning the set of cells from which water can flow to either ocean, right? Then here, as we run this BFS for the Pacific, Q and the heights in rows and columns, it will return the Pacific, the reachable cells to the Pacific Ocean. And in the same way we pass the Atlantic Q to the BFS and the heights in rows and columns, then it will return the set of cells from which the rainwater can flow to the Atlantic Ocean, right? Then we are, as I said, we are going to find the intersection of these two sets, Pacific reachable and Atlantic reachable. Then we need to return the list. So that this will be the complete solution for this problem. So this is very similar to the problem walls and gates and the rotting oranges. The same Q and the same BFS. In other two cases, we had the multi-source. But here we basically the water is flowing to the oceans, right? So let's analyze the time and space complexity. So space time complexity of this BFS approach is going to be O of m times n. M is here number of rows, n is the number of columns, right? And the space complexity is going to be O of m2. Yeah, that's it for this problem. And as I said, yeah, please go check another videos in this series for to see the pattern of this BFS with the Q. So definitely we can, for this problem, it can be done with the DFS, but this is more suitable for BFS because the water does not flow in one direction, right? Water flows wherever it can flow from higher elevation to the lower elevation, right? It just spreads as a BFS. That's why this problem is the good candidate for approaching with the BFS. Yeah, that's it for this problem. And if you have any questions, comments, please share in the video comments. And if you are liking this approach with a whiteboard explanation of the algorithm and the code walk through, and please like and subscribe and share with someone who you think might be helpful for. Okay, thank you guys, and I'll see you guys in the next video. See you, bye.